Good afternoon, dear comrades. I have a presentation to make on space experiment on the International Space Station with P-band SAR. Naturally, this somewhat is out of place or out of frame of what you discuss here, mostly on photogrammetry, but we also want to deliver accessible information for our clients. My name is Vladimir Stasevich. I represent a ROBIS company, but in fact I'm representing here a lot of organizations that include Institute of Radio Electronics, top experiment leader, Vega concern, the one that develops radar. UKB-ME provided a unique antenna. ROBIS handles the data processing, and we also want to contribute actively to data processing once we have those results. And our top expert on this matter, Andrei Zimov, will tell you what exactly we are going to do with the results once we receive them. And I simply must mention Energy Space Corporation as our supervisor, as our sponsor, without whom we cannot mount any equipment in space. Why did we determine on P-band? There are a lot of SAR satellites flying in the sky. This June, I attended USAR in Berlin, where they described how they can cover the surface of land with radars. Typically, these are shortwave X-band radars. I can understand them. I mean, it gives you good precision. But the other side, the reverse side of the precision, is the reflectance from surfaces off of the treetops or from the external layer of the ground. What's inside, we don't know. But P-band of 69 centimeters goes deep enough into the subsurface area. We can get information on objects under the ground, and vegetative cover is no obstacle. We can still recognize objects we are interested in, regardless of vegetation. I will show you a couple of examples here, how exactly what kind of information we can receive in different bands, different wavelengths on the same target site. As a sample, let's take a classical remote sensing unit that is an aircraft with 4 radars with different bands. This is what concern Vega can pride itself in. They mounted it on the 234 aircraft. So these are short specifications, XLP and VHF bands. On these images, one can see how much more information you can find in P-band and VHF band compared to L-band. These are areas with deeper waters. This is, for example, sea sensing results. As the wavelength increases, the detail of objects gets better, and we have more information about distribution of depth structures under the water. So, in order to implement this project, we needed, first of all, to obtain a permission to mount a radar on the ISS, and we got that permit. This is how the space station will look after we deploy the antenna there. It's quite big, 6 by 6 meters. So it unrolls in space when delivered into the hatch. Then it is attached and used together with other onboard equipment. So we're going to send the signal to the side of the station. Some characteristics of the radar, I will not name them. Now, what could we explore with it? What could we sense with it? First of all, it's soil, it's forests, sea ice and glaciers, in particular mountain glaciers. Unfortunately, P-band for space is deficiently studied. The European Space Agency plans to launch their first P-band satellite by 2021. To measure biomass of the rainforest. There are a lot of challenges here. So our first project with P-band will follow methodological purposes. We need to know how the ionosphere will affect the signal. We need to calibrate the radar. And we need to know the properties of the signal bouncing off different surfaces. We need to put together a signature database, off of which decryption will follow. But it should all be worthwhile. Ionospherical fluctuations create opportunities as much as problems. So operational control of this phenomenon around the station is crucial. And the space station flies all over the planet, all around the planet. So this way we will get some measurements of ionosphere. Of course, if we manage to use not only P-band, but several band radar in the future, to take into account Faraday effect. Also, we hope that data collected this way from P-band radar will be called for by defense and other institutes. The radar being constructed by Europeans is already prohibited over the territories of EU and the States. Naturally, the Europeans and Americans are afraid that you might spot a lot of interesting things there, so they're going to use it only over the rainforest. So before I pass the mic over to our expert on geological matters, I would like to invite everyone who wishes to know about this experiment, to participate in our development, by submitting your questions of interest. We've passed through the preliminary design stage, so you can make any changes to the equipment now. So if you're interested, feel free to submit your proposals. I'm referring to Russian and Chinese participants. And now I give the mic to Andrei Afanasyevich, who will tell us about how this can be used for exploration of mineral deposits.
Working on it.
I'll give you an example of how radar data can be used. Data from Almaz and Condor R is a decimeter complexes. Why do I accentuate this word potential component? When we discussed extracting data on depth structure,
Это новый паспорт?
it's important to know that this data is compatible to traditional remote sensing data. Of course, there is a good objection to it is drilling data. But this is a purely empirical experiment that generated a forecast map that was verified later by drilling data. So what is the essence of generations? This is a segment of radar data with which you can build a potential field. With which you can prospect for geological bodies. If we look at the structure, we will see model features, high resolution, medium resolution, or high frequency, low frequency, and medium frequency features. This is the basic geological map upon which you can build potential fields with sequential reconstructions of structural zones that have been subjected to geological verification. These are pseudo-seismic cuts on profiles that have been adapted to something more familiar for geologists, so that geologists could competently speak of the presence of such elements when drilling starts. This is a different ground. Well, let me go back and comment on these structures. Any geologist would say this is seismoacoustics that you can generate using seismic equipment, even though the source material here were remote sensing data. Radar data. Optical band needs to be reduced by determinant factors. I mean, vegetation, soil, fallen leaves, surface waters. Let me go back to the substrate to describe its potential. It's like the skin ripped off the body of the earth. It's kind of skeleton with muscles that produces the possibility of mineral deposits being laid there. So this is data from another ground. I will not comment on this too long. And the final thing we did is in Papua New Guinea is a digital elevation model based on radar data. We extracted geomorphological features. Anyways, I will not go into detail on these materials. But anyway, both X-band and decimeter band experiences lead us to a forecast with subsequent drilling, and all geologists know that the minimum meter cost of drilling is 100 euros. So if you reduce the number of meters, you can reduce the overall investment on such highly costly processes. Now, what can you do so that remote sensing data could be looked at as the potential field? This is the testing ground in Buryatia, where all the noise was removed from images from sensors, images from encoding, noises from encoding. This is the pseudo-potential field in its elemental representation. Here we can see areas of migration of geothermal solutions for geological forecast. This is done not manually, and these areas are original areas where we expected mineral deposits to seed, but the fieldwork only supported that forecast, and now actual operation has started on that site. So this is the prospects of radar data. This is the annual, these are nuggets from the cortex. The minimum cost of drilling is several dozens of millions of dollars. I don't say you don't need to do it, but if you deal only in resources and rare precious stones, this is a proof of being able to obtain those components. Thank you. This was quite interesting. I have a question. I didn't understand a couple of things. P-band has a long wavelength to have good resolution. You have to have better aperture. You see, all modern radar systems use synthesized aperture. Okay, all right, it's synthesized. I didn't hear the term SAR being used. That's the reason why I'm asking. And even X-band synthesizes aperture. X-band satellites fly in pairs. SAR and tandem X. Yes, exactly. I don't think they have too much of an aperture. They can hold the distance between each other. And the second question about prospecting of mineral resources, how deep can you forecast? Let me take this one, because if he starts answering, it will take hours. You know, if you do it even several centimeters, you can. Our methodology allows structurizing deposits 500 meters deep. No. These are different things. In reality, it's somewhat different. It's not exactly P-band. P-band provides its own information, it has its own benefits. It's just that not everyone knows how to process it. Not thinking about calibration, signature generation. With aircraft, it's easier, but when it goes through the ionosphere, I really don't know. All right, thanks. It was quite interesting.